Dave has set me up for kind of giving something new, something different. This is a talk that I give fairly frequently on the operational technology cybersecurity circuit. That's quite hard to say. So it is, a lot of it's recycled. But this is the great thing about coming somewhere new, is I've got a new audience and hopefully a message that you'll find useful and be able to take away and use in your own work. So I work for Rolls-Royce SMR Limited. It's a special purpose vehicle. It's majority owned by Rolls-Royce, but it's set up specifically with the intent of designing a nuclear power station built around the concept of a small modular reactor. And we're about, 7 years into that program now. And we're looking to get onto the grid sort of early 2030s. The program's funded, like I said, it's majority owned by Rolls-Royce. It's funded in part by investors and partners. So we're partnered with Constellation Energy, who operate the largest fleet of nuclear reactors in the USA. And we've also got £210 million worth of funding from the UK government to help us on our way. And that is enough funding for us to get to a design and get a what they call a design acceptance certificate from the UK's nuclear regulator to say, yes, your design is adequate, it's safe, you can build it if you want. The actual power station, sort of in the numbers, the site footprint, we're talking about 100,000 square metres. You could fit at least one unit under the Millennium Dome, probably two at a squeeze. So they are quite small as nuclear power stations go. The output is 470 megawatts electrical, and there's a lot of SMRs that are around that are all at the 300 megawatt mark, and that's kind of like an arbitrary limit for classification purposes. What we did is we figured out what's the biggest component in our nuclear reactor that we have to road transport, and that happens to be a pressurizer, and what's the height of a bridge over a UK motorway. And then we size the pressurizer to the bridge height, and then size the rest of the plant around the pressurizer, and that's how we got to 470 megawatts electrical. So rather than say 300 megawatt as an arbitrary limit, actually what is the thing that actually constrains what we're doing, and it's bridges. It's all module built, so the idea is that we manufacture all these modules in a factory environment, bring them to site, bolt them together. If you've ever driven past a McDonald's that's being constructed, and you go past one week and they're doing the groundwork, go past the next week and the thing's like done and they're fitting out, and you go past again and they're serving Big Macs in the drive-through. Someone from Rolls-Royce talking about McDonald's, I know. But it's essentially that construction technique. So everything comes prefabricated, bolted together. We've got to pour a bit of concrete, but essentially that's the concept. Okay, that's the sales pitch over. Unless it's a bit of a funny sales pitch, because unless anyone's got £2 billion in their back pocket, it doesn't tend to result in many sales. But if you happen to have a data center that needs 400 megawatts of electrical power, it's an interesting prospect because it's always on, it's low carbon, it's very reliable, it'll give you power for 18 months, then it has to switch off for a bit, and then it comes back on for 18 months. So the talk today is about the concept of secure by design, but how it is being developed and is being applied in the UK civil nuclear industry. So it's a little bit different to maybe sort of the concept within software engineering, but there is a lot of things that have been taken from software engineering and applied to what we're doing, and we've also learned our own lessons as we've been applying this. So I want to draw out some of those lessons and also talk about parallels with sort of network architecture and network security. Just to give a bit of background initially, to give you a flavour for what the technology is like that are in these power stations. The first civil nuclear power stations in the UK were the Magnox design, because the fuel was encapsulated in magnesium oxide. That's where the name comes from, Magnox. 1953, so that's all analog electronics and gauges and chart recorders and big rooms full of lights and dials and really awesome stuff, but very stupid, no software. late 60s, the advanced gas-cooled reactors started to be constructed and come onto the grid. Those are an interesting design because they're not pressurized water reactors, but their electronics is very basic. So there's a lot of analog electronics. Transistors were becoming useful sort of in the late 60s. So originally there was a lot of valves which later got replaced with transistorized electronics. But again, we're still talking very analog kit. You know, there's a resistor thermocouple, there's a resistance thermometer somewhere or a thermocouple that produces a voltage, and then there's an analog circuit that says, is that voltage too high? Yes, right, send another signal to another box that's going to open a relay and drop the rods in. Real basic stuff. Then 1980s, so you notice there's no 1970s. There were no 1970s in British nuclear. There was basically like, we did AGR, then we did nothing, and then we bought a US design in the 1980s, which is Sizewell B, which is a SNUPS, Standardized Nuclear Unit Power Plant System, power producing system. SNUPS is a backronym, but it's a US design. The electronics, again, basic. We've now got digital electronics, we've got integrated circuits, we've got a little bit of software. We're talking 6502 type technologies, you know, BBC type stuff, real basic stuff. The software isn't in charge of safety functions. It's there to help the operators manage the plant. So there's very little in the way of cybersecurity risk. But then we kind of get to today, and software has a much bigger role in safety of a nuclear power station. And that is both an exciting thing and a worrying thing, because there are a lot of advantages that it brings, a lot of operational flexibility, better performance. I'm not going to say it's cheaper because high assurance software is not cheap. Sizewell B, so the SNUPS, actually I told a lie. There is software doing safety functions on Sizewell B. The reactor protection system is actually software based. And I should have remembered this because we wrote the software. And it was done in Ada. So very strongly typed language, contractually based. You know, you can't use have to free vulnerabilities, all that kind of stuff in Ada. It really keeps you on the road, very strong guardrails in it. That is very high assurance software. It was very expensive to develop. It had to be went through formal methods, had to be mathematically proved to be correct. And it's been running that reactor for the last 20-something years quite happily. But obviously not connected to a network, not connected to definitely not connected to the internet. But now, yeah, we're seeing more software. So what's the role of operational technology in safety in nuclear? So this is a bow tie diagram. I really like bow ties. I think they're fabulous. They're a really useful tool. I encourage everyone to have a crack at them. So in the center at the top, we've got some kind of hazard, something that is bad that we don't want to allow to escape. So in your world, that could be data that you're trying to protect the confidentiality of or the integrity of, or it could be a network link or something. And in the middle, there's a postulated initiating event, which is a posh way of saying something that might happen, something that might go wrong. So a PI might be a temperature probe fails or a power supply fails, and that then leads to that hazard being unleashed. On the left-hand side, you've got all the things that you're doing to prevent that PI from manifesting. And in sort of operational technology land, if you want to align this to information assurance concepts, there's all this stuff about availability of your plant operating data to your operators, the integrity of that data, the freshness of it, so its authenticity. And then you've got things that you're trying to do to kind of limit what can go wrong. So if you think about how an Airbus flies, anyone familiar with the difference between a Boeing and an Airbus, apart from one stays in the sky and one doesn't? Right. So an Airbus plane takes instructions from the pilots, decides what's safe to do given the operating state of the aircraft, sort of how it's configured, what its angle of attack is, and all the rest of it. And it will then try and carry out that instruction within the limits of what is safe to do. So if you haul back on a side stick on an Airbus, it won't let you put the aircraft into a stall. And that's sort of one of the things that operational technology around a nuclear power station does, is it stops you from doing dangerous things. It maintains the operating rules of the plant. Now, the operators don't generally do dangerous things. They're very well trained, but it's just another layer of protection around preventing a hazard escaping. If your PI does manifest, you then get into sort of your response. And again, we're talking about availability of controls, so availability of data to initiate those controls, the correctness of that data, correctness of processing of that data so you get the right response, as well as it being timely. And then out on the other side, trying to keep all the stuff in, all the spicy clouds stay inside the concrete building, please. But you can sort of, if you think about NIST cyber assurance framework, it sort of follows that similar kind of identify, protect, detect, respond, sort of, and recover evolution. And you can use a bow tie with NIST if you want to. So what's the goal around secure by design? Security has generally been a risk management game, right? So you get given a system that some enthusiastic person, I'm not going to call them an idiot, but some enthusiastic person has designed a system. You get given it and you're told, make this secure. And you can't change anything about the design of the system, you just have to identify the risks and put in security controls to try and manage those risks. And ideally, you want integrated controls, you want operational controls, you want all that stuff on the right-hand side to try and tip the balance towards protection and away from risk, trying to keep it within the risk appetite. That can be super expensive, it can lead to unintended consequences. I know of a very large ship that belonged to a certain navy that hit the quayside because of a baseline cybersecurity control set. So the baseline, one of the controls in the baseline set resulted in that ship hitting the quayside, which is not a good consequence of trying to secure a system. But if there's another way, how else can we do this? Well, we can have less of this on the right-hand side if we have less of that on the left-hand side. But we can only control part of that equation. We can't do anything about the threat. Well, we kind of can, but we kind of can't. We tend to do it in a very negative way. If someone senior in your organisation gets up one day and says something very unpleasant about Xi Jinping or some other dictator, you're suddenly going to get a lot more traffic at your perimeter that might spoil your day. We can't really do much about the consequence, or can we? But we can do something about vulnerability. And this is where secure by design comes in. It's how we try and get rid of, or try and make that left-hand side of the equation smaller, so we need less of the right-hand side. And how do we do that? So there's a set of design principles. It's all the stuff that's obvious to me as a security engineer. I should probably clarify, I'm a security engineer, I'm not an IT security engineer. So I do physical and cybersecurity and procedural stuff and the whole remit around how you operate a power station securely. But you start with design principles that are obvious to us, but unless we communicate that to our engineering community, they'll have no idea. So we do that. We push ourselves into the engineering governance. So, and I'll cover this in a slide momentarily, it's not possible to release a product for manufacture unless you've actually done the right steps in the secure development lifecycle. That should seem obvious. It's obvious in software engineering, where lots of big organizations now have secure development lifecycles, but in engineering, turning bits of metal and all the rest of it, that's not occurred to the industry until about 10 years ago. And security is a default stakeholder in that process. We're in there by default. If you don't want security involved, you have to have a really good justification as to why your product has no security impacts. And we also do this sort of cross-domain risk management. So going back to that seesaw diagram, consequences is all safety related. That's what we care about in nuclear. Confidentiality, yeah, whatever. It's important, but it's not as important as keeping all the spicy rocks in the bin. So that's kind of what drives everything is safety. That's what tends to come out on the right-hand side of the bow tie diagram. So we do risk management with our safety colleagues, and we also try and work with the engineers to get the vulnerabilities out before applying controls. And we have this hierarchy of security controls, or security hierarchy of controls, which should be familiar to anyone who's done safety management. It's preferable to do the stuff at the top, try and eliminate that risk, get rid of it. If we can get rid of the risk, we don't have to treat it. It's done, it's gone. Brilliant, everyone goes home happy. If you're relying on operational controls at the bottom, that's not as effective, like anywhere close. The difference is, so if we were to take controls against malicious links and emails as an example, at the top we could say, well, we'll just remove all links from emails. That gets rid of the risk, but it can impact the business operations. So, okay, what we'll do is we'll substitute those links. We'll substitute them for links to a service that checks that the links aren't evil. That is better, right? It's a hell of a lot better than telling people not to click links in emails. That's the bottom. And we all know that works so well, because it doesn't, because people build business processes around it. So how we practice secure by design in the life cycle of a product. So left to right, we have these things called definition review gates. Essentially, it's a life cycle process that all these products go through, and it's a gated process. So DR0 kicks your work off, DR5 is released to manufacture. And to pass those gates, to actually get through that process, you have to have done certain security activities at the right time and have evidence from them. And we start, is this actually relevant security, through to have we actually controlled the risk to the point that we're happy. But in the middle is all the security support to the design. So I'm very lucky, I've got a big team. There's probably 12 or 14 of us, split between protecting the business and helping the engineers design the power station. And we provide lots of support to them during the design process and make lots of recommendations about things that they can do to the design to eliminate or substitute risks. That drives out most of the risk. And then what's left, we have to do dedicated security analyses to find that stuff, develop control sets that can then be applied to them, and validate those control sets to make sure they're not going to do anything weird like crash your power station into a quayside. What's the effect of this, sort of, in a very kind of nebulous way? All models are wrong, but some of them are useful, is the kind of health warning that goes with this. Also, if any of you have worked with STIX, Security Threat Intelligence Exchange, yes, no? Oh, I thought if there was any audience who knew about STIX, it would be this audience. STIX is a cyber threat intelligence serialization and exchange protocol. It's fantastic. I love it to bits, because it's not only is it great for sharing information about cyber threat, it's also really good for modeling. We've extended ours to include physical security threats as well, so it's not just cyber anymore. And it allows us to sort of create these models where we can say, here's a threat actor who's going to use an attack pattern that targets a particular asset on the power station. That asset is delivering a safety function. The attack induces a failure in the safety function, and that leads to safety consequences. Really simple model. The threat actor has a set of capabilities. That attack pattern requires a set of capabilities, so the threat actor can only do that attack pattern if they have the capabilities required to do it. Historically, that stuff on the left-hand side has been our domain in security. Stuff on the right-hand side at the top, that's been safety. Bottom has been engineering. Engineering make the vulnerabilities. Safety do something to deal with the consequences. Security try and prevent that from happening in the first place, by trying to introduce more controls to reduce the overlap between the capabilities required to deliver the attack pattern and the capabilities required by or possessed by the threat actor. If we can make those two separate circles, the attack can't happen. But what if we can just cross that line as security engineers? So we can kind of look at this as a whole thing and say, well, if we have some additional safety controls over here, the consequences of that attack are now mitigated, to the satisfaction of the regulator. It's now to the point that a radiological release is so unlikely that we're all happy and we can all sleep comfortably. What if we can cross the line into engineering and try and get that vulnerability out of the design? So we're more mobile around this space as security engineers in a secure by design approach than we would be if we were just left to, here's the design, go figure out the risks, put some controls in. So, I'm watching the clock. Lessons that we've learned in network security, examples that I've sort of found in network security that you guys should be familiar with. Things that you already do that are secure by design. So things like making sure that all your management traffic is out of band. It's not mixed in with the punters. Tunneling client traffic. Like, you don't know what's in there. You don't want to open it. If you can encapsulate it and keep it wrapped up and take it from A to B and never look inside the box, that's better than trying to process what's inside, because you've got no idea what it's going to do to your hardware. So you wrap it up, move it around, and you don't open it until it gets there. There's also sort of all the integrated security stuff. Integrated is better than dedicated. If it's integrated, it's much harder to get around than a dedicated security measure. Who uses a stop lock on their car or a crook lock anymore? Anyone even do that anymore? Unless you drive a really old car? Because all that security functionality is now integrated into the engine management system of the car. The software to run the engine will not run unless you've got a transponder in the key that has the right credentials to make the software work. That's integrated, and it's more effective than a stop lock, unless you're Jaguar Land Rover. That's another story. Or Ford had an oops as well. Learning curve, I guess. And you've also got all this stuff to support security controls that you're putting in. So span ports allow you to do network intrusion detection. Lessons that we've learned: being the default stakeholder is absolutely critical. Generally, most of the systems that we look at have some kind of safety consequence, therefore they're interesting to us from a security perspective. There are not that many systems on a nuclear power station that have no safety impact whatsoever, apart from maybe you can't even argue that a vending machine, right? Because if someone puts something in the vending machine that makes your operators sick, then that's got a safety impact. Pretty much nuclear power stations are strange and wonderful places. Do security early and do it often. So being part of that journey right away. I mean, that has been a really useful feature of that initial triage step. So whenever a project starts, project to design a product starts, they have to triage their product to decide, do we need security as a stakeholder? And then we get involved early and we can provide that engineering support during the design phase of that product and try and push out a lot of that vulnerability before it gets anywhere near sort of being manufactured or near a final design. Keeping us involved in design decisions has also been really useful. So we have like a formal design decision making process, which involves many meetings and minutes and is quite long-winded, but it generates evidence that we can use to support our decisions. So if the regulator comes back to us and say, why did you build this containment structure out of blancmange? We can explain why we did that. What was the logic that went into that decision? What was the evidence that supported that decision? Having security as a stakeholder in that decision-making process has led to a lot of really good gains. Things around hostile vehicle mitigation that's built into the landscaping of the power station, choice of materials in containment structures to make them more resistant to blast, all this kind of stuff. And being able to challenge the underlying design. We're not, security, we're not, when you watch a movie and you've got a character who's very passive, stuff just happens to them and then they have to deal with it. That's not our role. Our role is to be involved and have the ability to influence what's going on to arrive at a better destination than if we were just sort of being given the design and the risks and told to deal with it. So we're involved in the whole thing and we're able to challenge the underlying design and say, can we move this? Can we make this out of something else? Does this have to be software? can we use a relay to do the same job? You know, do we need a PLC? Can we just use a relay? Can we use a mechanical interlock? If we're going to use software, can we write it in Ada? Can we do something high assurance for this because it's so safety critical? Next steps for us now, though, so we're applying all of this stuff. We're generating the evidence that we need to support licensing. We'll earn our design acceptance certificate, touch wood. We'll get a first order, again, touch wood, unless anyone wants one for their data center. Any takers? No? Okay. But then beyond that, we've got other challenges that are probably more relevant to you guys in this room, which is around how do we provide off-site connectivity that's high assurance for doing things like equipment health monitoring, remote support, security operations center, because all these big power stations need cybersecurity operations centers, and emergency preparedness and response. One of the great conversations that I had recently was around telephone lines, with people telling me, oh yeah, we're going to use voice over IP, and then we'll get a bunch of analog telephone lines from OpenReach in 2030. Yeah, no, you're not getting telephone lines in 2030. You'd be lucky to get them today. And that's it. Establish your principles, support their application, be a stakeholder, try and drive out risk at source, and that's the main thing. The more risk you drive out at source, the less security you need, and that just makes everything better. Thanks very much.